Hello, everyone. I'm Jacob Stern. It's good to see all of you this morning. Good to see some familiar faces out there. I'm looking forward to teaching this class and learning together with you all. All right, so to start off, a little bit of background on me. Spoiler alert, I am not a professor, a BYU professor. I am a PhD student. So you're expecting a class taught by a professor with lots of letters after their name. You probably want to take it a different semester. On the plus side, I've probably taken this class more recently than any of those professors, and so I'm very familiar with the labs and hopefully can offer some help. And by focusing in on teaching a lot of the things that I didn't understand, which I had learned or had been taught more explicitly as I was taking the class. So yeah, I took the class in 2018, fall 2018, I want to say. I did my undergrad in ACME, Applied and Computational Math at BYU. And yes, any ACME folks out here? Yeah, woo. There are actually a lot of different majors that take this class, which I think is one of the coolest things. Just out of curiosity, what majors do we have out there in the room? So we have some ACME, I guess we have some computer science, a lot of computer science. Yeah, what other majors do you guys have? Stats, okay. Applied physics.
IS.
Pure math?
Information systems.
IS, cool.
Computer engineering.
Computer engineering, electrical engineering, I heard. Chemical engineering. Yeah, so this is awesome. This is really a great opportunity to collaborate and work with students from a lot of different backgrounds. And yeah, it's really a subject that lends itself to the intersection of disciplines. So that's one pretty cool aspect of this class. Yeah, so now I'm working on my PhD in computer science. My research pertains to chemistry applications of deep learning. So a couple of my projects and papers I've written are on protein structure prediction with deep learning, protein design with deep learning, and drug discovery and molecular docking. So if you're interested in those things, feel free to come and talk to me. That's kind of my passion. So, and I'll also probably talk about those things throughout the semester. Yeah, so without further ado, let's dive in. So first we have a quote from, let me get a background for that. Let's see. Yeah. And yeah, so I guess also, if you can't tell, this is my first time teaching a class. So if I talk kind of fast or seem a bit nervous, it's probably because I am. Hopefully that'll get better throughout the semester. But yeah, so to start off, we have a quote from Pedro Domingos, who's a pretty well-known AI researcher. People worry that computers will get too smart and take over the world, but the real problem is that they're too stupid and they've already taken over the world. And so we're going to talk a lot in this class about the theory and practical applications of deep learning, but we're also going to talk a lot about the ethics of deep learning and how we can make sure that we are using the technology for good instead of the technology using us. So this class, this particular class period, we're going to spend doing a pretty high-level flyover of what's going on in deep learning, what is it, where did it come from, where is it going, yeah, so let's get into it. So machine learning is changing the world. We have advanced robotics and surgeries being performed with the aid of AI. We have self-driving cars, and I think that picture's like 10 years old at this point. That's a pretty old looking Prius. We have speech recognition, drug discovery, learning on networks and recommender systems, chances are, even if you don't know it, you're interacting with AI and specifically machine learning on a daily basis. This is a snapshot from a couple of years ago of just a couple of industries that are seeing a revolution in deep learning. So we can see some more traditional deep learning applications, computer vision, robotics, speech recognition, but also starting to reach into other industries, healthcare, security, e-commerce. Here's a more recent updated version of that chart. And we see really AI and machine learning penetrating into almost any field. You have things from AI chips. So within this, you have accelerators for deep learning. You also have deep learning being used to design chips. You have a little bit of inception there. We have, agriculture, gaming, waste management. So tons of applications out there. And so I guess the question we're going to try to answer today is why? Why are so many people using these new technologies? And one answer to that question is money. So these are a couple of statistics and studies saying, trying to estimate the value of the deep learning market. In this one saying 20 billion by 2023, this one saying 40 billion by 2023, growing at 50% a year. Machine learning patents growing at a 35% annual growth rate. Spending increasing to, the numbers keep on going up. As we started at 20 billion, we hit 40 billion, now we're looking at 60 billion by 2021. So AI spending at least is outpacing expectations. Lots of companies selecting machine learning and AI as their company's most important data initiatives. So here's just a snapshot of a couple of startups that are out there. So Dreamcorp is a company that is using AI for insurance analytics, actuarial science, and trying to predict risk with AI. Analytic is a company that's applying deep learning to medical imaging and radiology, trying to analyze MRI and CT scans and digital pathology. Deep Genomics is a company working on DNA data, trying to understand the genetic causes of disease and possible genetic interventions. Isomorphic Laboratories is a company that actually just started last year. They were spun out of a company called DeepMind, which developed, which we'll talk about a little bit later, but which developed AlphaFold, which the chemists out here can probably attest is one of the most significant scientific advances of the last couple of decades. And some more applications. So this is this game is called Go, and it's not super popular in the U.S., but in the Eastern Hemisphere, especially Korea and China, it's a huge deal. And the same company, DeepMind, designed an algorithm called AlphaGo, which defeated the Go world champion, which was a pretty significant thing because the challenge of chess, which had been mastered about 15 years ago by AI, after that, Go was really the next big step, because though the rule set is simple, Go has a huge state space, much larger than the game of chess. And even today, masters of the game of Go are studying the moves of the world championships between Lee Sedol, the Go grandmaster, and AlphaGo, because the insights to be gained by watching this algorithm play were so significant. So these are some slides that I added. Most of the materials I want to give credit to David Wingate, who really developed the curriculum for this class. These are a couple of slides that I added because I think it's pretty important to know at least a little bit of where all this came from and where it started. So the first neural networks were invented, so to speak, in 1958 by a guy named Frank Rosenblatt. He published this paper on the perceptron, which was basically a mathematical analogy to a human neuron. But he wasn't able to really get any good results with it until, and so it kind of fell. It generated a lot of hype when he invented it, but by about 1970, they called it the first AI winter, where people kind of stopped getting funding to work on AI. But that changed in 1985 when two guys named Rumelhart and Hinton developed this algorithm to train these neurons, these perceptrons that Frank Rosenblatt had invented. So basically, the key idea that they figured out was how do you take this mathematical object and pair it with data and use that and train that mathematical object to learn relationships in the data. 1989, a guy named Jan LeCun came out with what was called LeNet, which is a convolutional neural network for handwriting recognition. You can see a little animation of it right there. And this was kind of the first real life application where we saw a neural network perform a real world task with pretty high accuracy. But after that, again, there was not a lot of further progress, and they called it the second AI winter. And the third wave of AI came along in 2012. So a guy named Alex Krzyzewski, working for Google, he figured out how to use a GPU, a graphics processing unit, to do massively parallel training and computation on convolutional neural networks. And he trained a very deep neural network for the first time. That's where the word deep learning comes from. And basically blew away the competition on an image recognition benchmark. And that kind of woke up the world and kind of told us like AI is here again, and it's really worth investigating. So then from 2012 to present, there's been kind of an explosion of deep learning programming frameworks, deep learning architectures, which are new ways of designing neural networks. Large language models, you might have seen, there are AI that can generate text that looks extremely realistic, and then lots more applications beyond that. So has anyone seen one of these curves before? This is what's called a hype curve. They're published by a company called Gartner Research, and they try to measure public sentiment on emerging technologies. So this is a hype curve from 2018, and right at the top, you can see deep learning. And that's, yeah, sentiment was high, and I would say that that's a pretty good estimate of when public excitement about AI was kind of at a peak. I tried to find this graph for this year, for 2020, but I couldn't find it. What I could find is an entire hype cycle for artificial intelligence. So that one dot on the curve has now become its own curve. And so the text is kind of small, but on the frontier here we have, I should also say, so x-axis is time, y-axis is expectations. And so at the beginning we have what we call the innovation trigger, where the technology is just starting, then we have the peak of inflated expectations, then you crash into the trough of disillusionment, and then gradually people, once reality sets in, they start to be able to develop like actual useful applications of the technology. And so we call that the slope of enlightenment and the plateau of productivity. And so, yeah, 2021, kind of this is, I think this is a great overview of the spectrum of deep learning technologies. So on the trough of disillusionment, we have autonomous vehicles, where it seems like autonomous vehicles are always a decade away. Computer vision, semantic search, which is related to understanding the meaning of images and text. At the peak, we have edge AI, which is like AI on your cell phone. I don't know if any of you heard, but the latest Google phones, they have a dedicated chip for AI. So performing AI on a device instead of, or on a radio tower instead of in the cloud. That's edge AI. We have transformers, which are a certain type of neural network that have gotten really good at generating text. And then over here on the far left side, we have artificial general intelligence, which is kind of an umbrella term for, yeah, AI is great and it can do really well if you give it a very specific application, but we want general intelligence that can flip hamburgers and hold a conversation and come up with new scientific hypotheses and do everything kind of at a human level. Also over here we have physics-informed AI. This is kind of where my research falls, and yeah, that's definitely an area that's on the rise. Yeah, if you're interested, I'm going to post these slides after the lecture, and so you can look at more of those and research them more in depth if you're interested. Okay, so these are a couple more visualizations of the growth of AI. So this is the number of archived preprint research papers on AI through 2017. And you can see exponential growth there. Google project directories for code. And then this one doesn't look exponential, but then if you look at the y-axis, it's a log y-axis. And so it is exponential. And this is the amount of computation time necessary to train the latest and greatest neural networks. So the question is that growth justified? And to answer that, I have a short clip to play. I'm not sure how to make the audio go through, but we'll just go off of this. All right, so obviously I'm teaching this class. I'm devoting my career to researching deep learning, and so I'm sold on the practical application and usability of deep learning, and we'll see if by the end of the class you all agree. So what is deep learning? If we're going to look at sets and supersets, so as in the largest umbrella, we have general artificial intelligence. Within that, we have a class of algorithms called machine learning, which are algorithms used to, like computer algorithms used to achieve artificial intelligence. And deep learning is one type of machine learning algorithm that's very useful for specific applications, which we will discuss. And so I think this is a really good intro to how, if you aren't familiar with machine learning, to how machine learning works. So basically you have training data in the form of text, images, etc., labels associated with that training data, and then you have to convert that training data into some type of numbers, what we would call feature vectors, or lists of numbers that you can feed into a machine learning algorithm. And And that algorithm will train a machine learning model to learn the relationship between those images or text and the labels. And you can then take that trained model and take new text and new images, etc., convert them into numbers, pass them through that model, and predict expected labels for that new data that you do not have labels for. And we'll look at some specific examples of that. We'll skip that. So we're going to spend a little bit of time talking about the biological inspiration and show how that translates into the math of neural networks. So here we have a diagram of a neuron. Thanks. So this is the side of the neuron that takes the inputs, and this is the side that produces outputs. So on the input side, we have these tendrils called dendrites, which carry impulses towards the cell body. They are combined and then transmitted through an axon to the axon terminals, which then distribute that signal to other neuron cells. So then how does that translate to math? So we can take our input data, which we'll call x naught, and we will call that an axon. One of these, an axon or an output from a previous neuron. Then we have a weight, which is called a synapse, which is not in this diagram, but it basically is a weighting function on that input data from the axon. And then we take synapses from multiple other neurons and then combine them in a simple weighted sum. So we have the weight times the data, and then for each of the inputs, then we sum up all of the inputs. And then you apply what's called an activation function, which can be kind of like an amplifier or a muffling function, and that produces an output, which is passed on to the next neuron. And so another key idea to understand is, especially with relating to deep learning, is this idea of layers. So this is a diagram of the human visual cortex where signal enters through the eye and originally lands right here at the first level of the visual cortex. That level performs a little bit of computation and passes on kind of a combination of those features that it learned to the next level, which is more computation and passes them on to the next layer, et cetera, et cetera, et cetera. And neural networks are designed similarly. And the really powerful thing about layers is that you can learn hierarchies of features. So for example, if you think of, let's see, what's something we can look at? This tissue box right here. You can imagine that a certain layer, one of the earliest layers of our visual cortex, might learn to recognize coarse-grained patterns or shadows. And higher levels of our visual cortex might learn to recognize shapes like this cube. And even higher levels of our visual cortex might learn the relationship between a cube and a tissue means a tissue box. And so this kind of idea of hierarchy is a really powerful idea that our brains use, which we also take advantage of in neural networks. So, and this is kind of a classic example of how we would diagram those layers of a neural network. So here would be our input data. Here, these arrows represent synapses or weights. So those W's, those weighting functions, those are these arrows. And then that produces the axon outputs for the next layer, which are then passed into new synapses, which produce axon outputs for the next layer. And then we have more synapses, which produce our final output. they can get much more complicated. So this is, I think, a cool video that demonstrates kind of what's at play inside a neural network. So you can see as different inputs are passed through, different synapses light up, and eventually leading to synapse corresponding to the recognition of a specific written digit. So the first two videos that it just showed are what are called fully connected neural networks.
So that's basically how neural networks work. You stack more and more layers, which allow you to learn more and more complex or abstract features from your input data. This is a diagram of the neural network used by Alex Krzyzewski in 2012 in the AlexNet neural network that kind of kicked off this latest wave of deep learning. And that's about it. Any questions? Also, of course, we're going to go more in detail in this class. But today, I'd like to kind of give you a sense of why these deep neural networks work so well. So previous statistical models or machine learning models have been able to learn simple patterns or clusters, whereas neural networks are able to learn deep hierarchical patterns. And for certain problems, for example, problems where you're dealing with extremely high dimensional data like images, you really need some sort of model that can learn those much more complex relationships. So there's a paper that in fact shows that neural networks can approximate any function given enough training data and given a neural network that's wide enough or deep enough, a neural network can approximate any function. So if you think about the problems that you're facing in your company or in your research, and if you can frame those problems as function learning problems, a neural network can solve that problem. And that's provably true. Of course, there are going to be some caveats to that statement based on the constraints of how much data you have. But the theoretical properties of neural networks are very strong. So now let's take a look at a couple of cool examples of how neural networks are performing really well. So this is the AlexNet 2012 paper. So prior to then, previous methods would take an input image. They would hand engineer features out of that image by edge detection algorithms and things like that. Those features would be passed into a simple machine learning model, such as an SVM, support vector machine. And that model would be trained to predict what was in that image. Enter AlexNet in 2012. All of that hand engineering of features and the simple model are replaced with an 8-layer neural network with 60 million parameters. And we train it, and it learns with much higher accuracy to predict what things are in that image. Now, of course, if you look at what it took to train that, this network had 60 million parameters and 1.2 million training images. Now, not every problem has those. And so we'll discuss throughout this class how you can make use of less training data. And so this is a visualization of those results. So prior to AlexNet in 2012, progress was pretty flat. This is the ImageNet benchmark, and we're tracking error rates over time. 2012 AlexNet dropped the error rate by about 10 absolute percentage points, and which is like a 30 or 40% relative improvement. And from then on, everyone else caught on, started using deep neural networks, and as of 2014, the error rate was down around 7%. I think most recently, it's more like 4%, and human error rate is about 5 or 6%. So right now, these models are doing better than human accuracy. Another example of an application where deep learning has made waves is speech recognition. Up till about 2010, people were using traditional machine learning models with hand-extracted features. Enter deep learning, and immediately error rates start dropping dramatically. This is an interesting visualization of kind of how impactful the AlexNet insight of using GPUs was for increasing accuracy based on compute. So you can see that CPU performance is basically flat over the last 10 years, and that is frequently called the end of Moore's law, where the exponential scaling laws that CPU compute followed for so long are finally starting to slow down. On the other hand, AlexNet took advantage of GPUs, which use massively parallel computation. And in part driven by demand for deep learning, you can see the amount of computation available per dollar has increased exponentially in the last 5 or 10 years. So going from about 5 gigaflops or 5 or 10 gigaflops at the time of the AlexNet paper to as many as 40 gigaflops in 2017. And now it is in 2022, it's much higher than that. So here's another cool example. This is a recommender system, a Spotify recommender system, trained to listen to songs and predict whether you will like that song. So on the left, you have what's called a spectrogram, which is basically a way of recording sound. And the neural network learns in different neurons to recognize different patterns. So filter 3 might recognize Christian rock. Filter 15 might recognize a cappella mixed with smooth jazz. Apparently that's a genre. Filter 26 learns to recognize gospel, 37 Chinese pop, and so on. And from all of these recognition filters, the neural network can build up a representation of this song. And similarly, based on your interests, a neural network can learn a representation of you, and between its representation of you and its representation of the song, it can predict how likely you are to enjoy that song. Here's another company doing really cool things, Lyrebird. They are a company that basically records your voice footprint or your voice fingerprint and allows you to speak with your own voice again after losing it. Another popular application where neural networks do really well is natural language processing. So this is an example model where we take as input the text of an Amazon review, and the neural network is able to predict with 96% accuracy whether that review is positive or negative. And then it can predict the actual number of stars with about 75% accuracy. Another example of AI being used for good is this tool that Google released using AI to quickly identify child pornography or child sex abuse images and remove them from the internet. These are two extremely impressive examples of AI being trained to play video games. So in April 2019, OpenAI released a model that was able to play Dota 2 at an extremely high level and defeat the world champion team. And a little earlier than that, DeepMind had released a model trained to play StarCraft 2 extremely well. This model was called AlphaStar, and I believe they beat the top players in the world in 4 out of 5 games. And these are extremely complex games that were kind of seen as grand challenges, and we see AI and specifically deep learning rising to the challenge and performing extremely well. Going back a couple of decades, we have a model trained to play Atari, and again, do extremely well. I think this particular model was trained to play all 57 different Atari games. So this is kind of a different challenge. Rather than having one very complex game, you want to be able to generalize across 57 different games. Playing poker, again, this is a model trained to play poker and was able to beat several poker world champions. So I think you might be catching the trend that basically if you can pick a specific task and train a neural network to do it, it can do it at basically human performance. One of these other tasks that may not be as obvious of an AI problem is generating images. So there's a whole family of neural networks called generative models, which are trained to, rather than trained to predict labels for data, they're just trained to generate images similar to images in the training set. And so this is a model called Big GAN, and GAN stands for Generative Adversarial Network. And you can see that it's able to generate very visually impressive photorealistic images of animals, food, plants, even bubbles. This is another pretty cool generative model where it allows you to paint a very coarse landscape, and then it will find a photorealistic version of that landscape that that matches your drawing. So you can start to see the applications of some of this technology for animation and for movie making and things like that. We'll end today with one more example of a neural network that's trained to label video. So you can see this is a video of a car driving down the street, and a neural network was trained to identify and label each pixel in the image as belonging to a car or a tree or the road or a pedestrian, etc. And you can see the obvious applications of this for things like self-driving cars. This is kind of a fun one on the right, where you see a pose is extracted from an actor or actress on the left and transferred to the person on the right. And we'll see a fun clip of this. So you can see these people on the right have suddenly learned these amazing dance moves from this professional dancer on the left. So fun stuff. So that is all for today, and I will see you next class.